Hello guys, welcome to Physics Grad. This is the second video on Legendre Transform, and in this video we are going to see how to mathematically formulate our Legendre Transform for the case of a convex function. Alright, so let's begin. Previously we saw that any convex function can be represented in two ways. The first way is to represent it as a set of points x comma f of x in the xy plane, which gives the curve of f of x, and the second way is to know all the family of lines to which our curve f of x is going to be the envelope. Okay, and these family of lines are nothing but the tangents to this curve. So if we know all of these tangents, we can calculate the equation of the envelope, which means we have all the information about f of x. So these are the two ways of representing a convex function. Okay, now the question we are trying to answer is that if we know 1, okay, how to go to 2, how to get 2. So this process is done by using Legendre Transform, as we have seen in part 1 of the video. Okay, so what do we need to get 2? We need some way of representing the tangent lines. Okay, so how do we represent any line? We know that any line is represented by the equation of the form y equal to mx plus c. But this describes any random line. But what do we need? We need only those lines which are tangents to the curve defined by the points x comma f of x. Okay, that is what we need. So this equation can be written as minus c equal to mx minus y, right? All right. So this implies to know the equation of the line, the only information that we need is the value of m and the value of c. Okay, so if we know the value of m and minus c, the reason why I am taking minus c is because of a convention which will be clear later on. Okay, but it doesn't make it any there is no ambiguity here, because if you know minus c, if we take a negative of that, we know c, which means we know the equation of the line if we know these two parameters. Okay, so if we know the values of m and c, we know the line. So all that we need to know right now to get the equations of tangents is to know the value of m and c for all the tangents. Okay, or more specifically m and minus c for all the tangents. That is what we have to find. Okay, so this implies we need to know the set of tuples m comma minus c corresponding to all tangents, corresponding to all the tangents. This is what we need. Okay, so how do we find this? Okay, how do we find this set of m and minus c? So to do this, let us observe the following. Let us say we have our convex function which looks something like this. All right, now what I do is I choose a particular m. Okay, so what we'll do first, so consider a convex f of x okay, and choose some m naught, that is some value for the slope. You just choose it. So once we choose this, there are infinitely many possibilities for the value of minus c, okay. So choose some m naught. This implies there are infinitely many choices for minus c, okay, corresponding to infinitely many parallel lines. Infinitely many parallel lines. Okay, so what do I mean by that? So once we choose our m, then there are infinitely many lines that I can draw, okay, in this manner, where corresponding to each line we get different values of our intercept values c. But what we see is that for a given m naught, okay, so the slope is m naught for this, we see that there is only one line, that is this one, which will be the tangent. Okay, there is a unique line in this set of infinitely many parallel lines which will be our tangent. Okay, so what do we have to write here? But only one of these lines is going to be the tangent. Okay, let minus c naught be the corresponding negative value of the y-intercept. Okay, then our equation of the tangent, would be minus c naught equal to m naught x plus minus y. Okay, but for this to be a tangent, it must touch the f of x curve at exactly one point, and let this point be x naught comma f of x naught. Okay, then our equation, since this line should contain this point, the following equation must be valid. Okay, and apart from this, we know that slope of the curve equal to slope of tangent at point of contact. This implies slope of the tangent will be equal to the slope of the curve at the point of contact. Okay, so all this taken together, we have the following: minus c naught equal to m naught x naught minus f of x naught, where m naught is given by the slope of the curve at the point x naught comma f of x naught. Okay, so therefore, so let me write it. Therefore, to get minus c naught, okay, we used the fact that first x naught f of x naught must lie on the line, okay. 2, that m naught must be equal to d by dx of f of x at x equal to x naught, okay. So if these are satisfied, then our tuple m naught comma minus c naught is going to be the tangent to the curve at x naught comma f naught, okay. So these, if satisfied, okay, the tuple m naught comma minus c naught represents tangent to f of x curve at x naught comma f of x naught, okay. So what have we done here? We have first chosen a particular m naught, and then we have we are choosing, or what we are doing is, by varying the value of the intercept, at one point this line is going to touch or be a tangent to the curve, and since the line, we want to find the line which is the tangent, the condition for the value of c naught is going to be the one where a particular point of the function, which we call as x naught f of x naught, okay, must lie on this line, and the slope of this line should be equal to the slope of the curve at the point of contact. So using these two facts, we can calculate the value of c naught, okay. And once we know m naught and c naught, okay, we know the equation of the tangent at the point x naught comma f of x naught, okay. So that is what we have done. So similarly we can choose some other m1, and we can correspondingly find minus c1, again m2 minus c2, and so on, by following the same procedure, okay. So once we get these points, which are m comma minus c, which is equal to the set of points m naught comma minus c naught, m1 comma minus c1, and so on. There are infinitely many such points corresponding to each of the tangents, okay. Once we have these points, we can make a plot in m versus minus c axis, okay, because minus c is a function of m, okay. So what I am saying is that we can represent all these points, okay, in a two-dimensional coordinate system where x-axis denotes the m and y-axis denotes minus c, and I can plot. So if this is m naught and minus c naught, so this point, again all the points I can plot in some way, and this will form a curve, okay. That is what this particular statement is saying, okay. So to see the fact that minus c is in fact a function of m, okay, so to see this clearly, consider the case where f dash of x is invertible, which means f dash of x is a 1-1 function. Let us just consider this case just to make just to understand this better, okay. If this is the case, this implies since m naught is equal to f dash of x naught, Okay, this implies x naught is going to be f dash inverse of m naught, okay, from this relation. So our equation for minus c naught will now become m naught into x minus f of x naught, which, so m naught into x naught minus f of x naught, which is now going to be m naught into x naught is replaced using this equation, f dash inverse of m naught minus f of f dash inverse of m naught. Okay, so we are starting with our knowledge of the representation of the function we using the points x comma f of x, which means we know the function f of x, which means we can calculate f dash of x, which means we can calculate f dash inverse of x, inverse of some quantity. Okay, so if f dash is invertible, clearly this c naught is expressed as a function of m in this manner, and therefore we are going to write c minus c in our y-axis in this space. Okay, all right. So the procedure is we choose a particular m, get corresponding minus c for the tangent using minus c is equal to m into f dash inverse of m minus f of f dash inverse of m. Okay, so in this case where f dash is invertible, using this particular relation we go from f of x comma f of x to minus m comma minus c. Okay, so this becomes our Legendre transform. So to make it more clear, okay, let's call minus c as g of m. Okay, then all the points m comma g of m, okay, will represent a curve in m versus g of m space. Okay, that means we have g of m, and all of these points will correspond to some curve. Okay, so this g of m is the function that we get when we apply the Legendre transform to f of x. Okay, so then how to formulate this mathematically? Okay, so how exactly formally do we get this relation? Okay, so let us look at that. So choose m equal to m naught. Okay, and we need to get the corresponding minus c naught. For this, consider the function m naught x minus f of x. So this is a function of x. Okay, let's call this h of x. Okay, then for what value of x does this h of x have a maximum? Okay, so to do this we will have to differentiate h of x with respect to x and equate it to 0. So that is d by dx of mx minus f of x, which implies m minus f dash of x should be equal to 0, m naught in fact, which means m naught should be equal to f dash of x. Okay, for what? For h of x to be maximum. Okay, so which implies if f dash is invertible, if f dash is invertible, h of x has maxima at x equal to f dash inverse of m naught. Okay, so we have already seen that the f dash inverse of m naught is nothing but x naught. So this should be equal to x naught, which means our h of x at x equal to x naught, that is at the value of x where there is a maxima, becomes m naught into x naught minus f of x naught, where our m naught is f dash of x naught from this relation, and x we found that is equal to x naught. But this is exactly the same relation that we get for our c naught. So if you, where is that equation? Yeah, so if you notice this equation and this equation, okay, we will see that h of x, x equal to x naught, is in fact equal to minus c naught. Okay, so we got minus c naught as equal to the value of the function m naught x minus f of x at the value of x where this function takes a maximum. Okay, so this is the formal definition of our Legendre transform. Legendre transform. Okay, now before we conclude, let me just make sure that this in fact has a maxima. So for a function to have maxima at a critical point, its double derivative must be greater than 0. So in this case it is our function h. So h double dash must be greater than 0 for it to have a maxima, and our h double dash is nothing but d by dx of h dash, which is d by dx of m minus f dash, which is f double dash, and f double dash, since it is convex, we know that it is always greater than or equal to 0. Okay, and therefore if we consider functions which are convex, which are such that f double dash is greater than 0, then h double dash is also greater than 0, which means it is going to have a maximum. All right, so what are we getting here? Our function g of m, which is equal to minus c, is got by the following transformation, where we find the value of this expression at the point where it takes the maximum value. Okay, so that is what this particular operation tells us. So this implies evaluate mx minus f of x at the value of x where mx minus f of x has a maxima. Then the corresponding value of this function is going to be the value of minus c for the corresponding slope x. Okay, so this is our equation which represents the Legendre transform. So what is the equation? G of m is equal to max, the value of mx minus f of x at x, where mx minus f of x takes the maximum. Okay, so this is our Legendre transform. So of course this is a special case where f of x is a convex function, and we have considered lots of assumptions here. So therefore this is not a very rigorous definition, okay, because this is not a general case. A general case would be taking our x from some particular set called the convex set, okay, and we have not considered all that. We are just doing this from the physics perspective. But if you go deeply into the math perspective, there is much more to this than just taking maxima of this function, okay, because in that case the value mx minus f of x will belong to some kind of a set, and instead of taking the maximum of a function, you will have to take something known as a supremum of the set, okay. So that is if you want to make this more rigorous, but for our application, this much of a definition is, or this much of a formulation is more than sufficient, and this is where I would like to stop, okay. And in the next video we are going to see some of the important properties of Legendre transform. So see you next time. Thank you.